In this set of notes, we're going to start talking about assessing model adequacy. So in other words, we're going to start talking about checking all of those assumptions that we've been referring to whenever we talk about confidence intervals and hypothesis test. And it's unfortunate, but I often see in analyses, people will run regression analyses, but they never check the assumptions. And so I really want to highlight the importance of going through these steps. And the reason for this is if you've violated your model assumptions, then the results that you come up with may not be valid. And so it's a step that often gets overlooked, but is crucial. And I think part of the reason that it gets overlooked is because we often don't include this step in our articles that we write or reports that we write up. It's not something that we generally include, and if we do, it's usually just one sentence, but a lot of work can go into checking whether or not these assumptions have been met. And so what I hope to see in the future, and some publications are starting to do this in the open science framework, is that even though this information isn't necessarily included in the article, I'm hoping in the future to see it in the supplemental materials so that we know the results that we get from a model or from a particular method, and this isn't just for regression, this goes for any statistical analysis you would perform, that the assumptions that make that analysis valid have been met. Alright, so to check the assumptions for regression, and we've talked about this in the past, what we're really going to do is we're going to be looking at the error terms. And so remember that we've made this assumption about the error terms and their distribution. So in other words, we've made the assumption that they're distributed normal with mean 0 and variance equal to sigma squared. Now this is one of the assumptions for linear regression. Another common type of regression that you may encounter in your own work is logistic regression. Logistic regression has a different set of assumptions on the error terms. So that's what makes these different types of regression different, and it's one of the reasons that this assumption or these assumptions are so important. So just as a reminder, so what we could do here is we could consider the model. We could solve for the error terms, and so we use the regression residuals to estimate those unknown errors, and we've talked about this before in the past. And notice here the regression residuals do have the hat on them, and because these are estimates, we're using our fitted model or our prediction equation to obtain these. All right. So here's kind of a picture of what is happening. Here we have the true model. So this is that true unknown model that we don't know. And here is that estimated model, or you can think of this as that prediction equation. So when I say the true model is unknown, what I mean by that is we can specify the model this way, but we don't know what the exact value of these parameters is. So here in this picture what we have is these are just some typical observations that we might see. And so the idea that the true error, what the true error is equal to, is the true error would actually be the distance between the true model and the observed point, whereas the residual, on the other hand, the residual is the distance between the estimated model and the observed point. And what we're doing is we're using that distance to estimate the green distance, or the distance that we're actually interested in. Alright, so there's a couple important properties of regression residuals. And so you'll want to take a moment, pause the video and read these, but the two main ideas here are the highlighted pieces, that the mean of the residuals is equal to 0, and we've talked about this before, and that the standard deviation of the residuals is equal to the standard deviation of the fitted model. Alright, so we had this example from Module 6.3. This was the animus example. And so recall this data set contained observations from 196 different media markets, and we're going to look at a regression model related to the following dependent variables. So we have 4 different dependent variables or predictor variables. Right. Here is our output. So you'll notice for each of those independent variables we have our estimates. And then here we also have some output, and this is where we can see those different residuals. So notice here we have the observed value of animus for each of our 196 different observations. This is the value that for each of those observations, for example, if we looked at observation 196 and we looked at the level of its value for the 3 independent or predictor variables, this would be the predicted y. And so you'll notice that the residual is going to be the difference between the observed value and the predicted value. So the first thing to notice here, when we look down below, notice that the sum of the residuals is equal to 0. So this is that first property that was in that box up above. The other thing to notice here, if we look at the sum of the squared residuals, okay, have a look at this value. And now let's go back up to our model summary that we had up here, and notice this is the same as the SSE of the model. So those are the 2 different values. So just to summarize what we're seeing here, going back down, is this is the property 1 from the box up above, and this is property 2. So we can use our residuals to help us detect lack of fit of our model. So the first assumption that we have is that the expected value is equal to 0 for any given set for the explanatory variables. So if that model is specified incorrectly, that will not be the case. So in order to detect model lack of fit with residuals, we can look at any of these 3, or probably any of these 2, and there's a note down at the bottom. So we could plot the residuals on the vertical axis against each of the independent variables. We could plot the residuals on the vertical axis against the predicted values on the horizontal axis. And then for each plot, we're going to look for trends, dramatic changes in variability, and or more than 5% of the residuals that lay outside any 2 standard deviations of 0. All of these patterns may indicate a problem with model fit. So here we have that example from module 6.3 again. Alright, so looking up at our 2 different types of plots. Plot 1 that we see right here is going to be this plot. So for this plot, notice we have the residuals on the vertical axis. Oh, sorry, I've said that backwards. This one is plot 2, not plot 1. So we're going to plot the residuals on the vertical axis against the predicted values on the horizontal. So again, we're going to look for trends, dramatic changes in variability, and more than 5% of the residuals that lay outside 2 standard deviations. So looking at this particular plot, I would like to examine these poo points right here to see if they're outliers, and we're going to talk more about outliers in the next module. But overall, this doesn't look too bad. We've got fairly random scatter, about 0. There might be a slight pattern here, but I'm not too concerned about that. It's not very pronounced. Now the other type of plots that we might look at is the first type. Those are actually going to be the ones on the next page. And so notice for each of these plots what we have is the residual on the vertical axis, and then we have each of our independent or predictor variables on the horizontal axis. We had 4 different predictors, so we have 4 different plots. Now again, we're looking for any kind of pattern, changes in variability, things that might be concerning. So looking at these, notice here, if we look at this plot right here, it looks like the variability on this end is much lower than the variability here. So we see kind of this funnel shape. That might indicate a lack of model fit, and that's probably something that we're going to want to explore. Whereas if we look at this plot, we see a little bit more random scatter, and if I look at the amount of variability, it does appear there's slightly more here than there is here, but it's not as dramatic as the other one. So these are all things that we want to keep in mind and check for. And looking at the scatter plots is usually a visual check. It indicates that we might want to go in and look at something further. So it's by no means, the end-all check. We don't look at these and just throw our model out the window. Here's another example. Consider that AIDS HIV example from the Module 8.3 notes. And so let's see what happens when we fit a linear model to something that was obviously a quadratic relationship between years and number of deaths. So again, this is the number 2 plot that we referenced up above. This one is the number 1. Notice in each of these we're seeing an obvious pattern in the residuals. Here we definitely have a lack of fit. Whereas in the first example, we may have a lack of fit. It's something we want to explore. From this one, we can definitely see from these residual plots that we have a lack of fit, and we need to explore this and see if we need a different model. And we actually saw with this example that we do need a different model. We needed that quadratic model, not the linear model. Now, for each of these, for this example up here, notice that we had 4 different predictor variables. So in other words, we were looking at a multiple linear regression model. When you work with multiple linear regression, looking at these scatter plots can be worthwhile, but one of the things that we might want to consider is we might want to say, okay, for example, if I'm interested in those over the age of 65, what is the effect of that variable without the other variables? In other words, holding those fixed. Because notice the residual is going to take into account all the other variables. So you can look at what are called partial regression residuals. And so these are really good when you're looking at multiple linear regression. Partial residuals measure the influence of xj on the dependent variable y after the effects of all other independent variables have been removed or accounted for. So if I was interested in the percentage of the market that was over 65 as my independent or predictor variable, what the partial regression residual will do is it will actually measure the influence of that variable while taking the other 3 independent variables either removed or accounted for. And so here is the formal definition of a partial regression residual, and I'm going to have you read this section on your own. So again, if you're performing multiple linear regression, the partial regression residuals are something that you're going to want to consider. One of the other assumptions that we need to deal with is the one of constant variance for all levels of the independent variables. Variances that have this property are called homoscedastic, whereas unequal variances for different settings of the independent variable are said to be heteroscedastic. When the data are not homoscedastic, the reason is often the variance of the response y is a function of the mean. And so here we have 3 different possibilities to consider, and we have what those plots may potentially look like under those 3 different scenarios. So again, pause the video here for a moment, read through these different scenarios, and see the transformations that may be used. Alright, so let's look at an example. So data on age and years and plasma level for a portion of 25 healthy children in a study are presented in the table here. So we have age and we have plasma level. First, let's consider a straight line model using age to predict plasma level. So here we have the output from our regression analysis, and now we have our residual plots. So let's look down here at the residuals for plasma. So we have age by the residuals. Notice that on this side of the plot we have very large variability. We have smaller here. So this suggests that megaphone shape. So looking at this, we don't have equal variances for different levels of the explanatory or predictor variable. So we might want to consider a transformation. And so since this is the megaphone shape, if we go back up to some of our suggestions that we have here, notice here we have the megaphone, and for the megaphone we might want to instead look at the natural log of y. So here in the data set, I've also included the natural log of y. So if we scroll down, you'll notice here is the output with the logarithmic transformation. So we do get a different model. And now let's look at those residual plots. Notice here the residual plot looks much better. We've taken care of some of that variability. Is it exactly equal? No, but it is better than it was before. So the transformations are not going to be a fix-all, but they are going to help some. Now we do need to be careful when we transform our data. So we can now use our regression model to predict the natural log of y. So that second confidence interval, or that second set of output is predicting the natural log of y, not predicting y. So we have to be very careful here. So consequently, the predicted value of y is the anti-log of y hat. So we can transform the endpoints of the prediction interval back to the original scale, and the interval will still retain its meaning. But you cannot take the analogs to find the confidence interval for the mean value. So this is one of the tricky things with transformations. If you use a transformation and you fit your regression model, you can still find confidence intervals and prediction intervals, but they're all going to be in terms of the natural log of y. That's what you're going to be predicting, and that's what you're going to be estimating the mean of. You can back transform to y the prediction intervals, but you cannot do the same thing for the confidence intervals. So this is the reason that the mean value of natural log of y is not equal to the natural logarithm of the mean of y. And so this is a very important piece in terms of our predictions. We want to be very careful anytime we take a transformation. So looking here at our output, what we're saying here is we've got our two different intervals. We've seen prediction and confidence intervals before. This one we can't transform. This one we can transform. So if we want to, with 95% confidence, predict, so make a prediction interval, for the plasma level of a healthy child who is 3 years old, this is something that we can do based on that model that predicted the natural log of y. And so how we would do that is to find the interval. We're going to transform the prediction interval for the natural log of y. So in other words, we're going to take our two endpoints. We're going to take e to the 1.6001, e to the 2.2128. And this is going to give us the interval 4.95 to 9.1417. And then we can write out our usual interpretation. So we predict with 95% confidence the plasma level for a healthy child who is 3 years old will be between 4.95 to 9.1417. So again, this works for prediction intervals. We could not do this same thing for a confidence interval. There are also hypothesis tests one can use to check for heteroscedastic variances. However, all these tests assume that the errors are normally distributed. So in most cases, the graphical procedures are sufficient to assess whether the errors are homoscedastic. But again, you could use one of the hypothesis tests as long as you're confident about the normality assumption. So I have some comments here on the normality assumption. I'm going to let you read through those. It is the least restrictive of the assumptions when you apply regression analysis. In other words, it usually is fairly robust. There are several different tests. Usually, if you're going to do a visual assumption, you would use histograms, stem and leaf plots, or normal probability plots. And those are usually used for smaller data sets because the histograms and stem and leaves may not be as reliable. So this is going to end this note set, and we're going to continue talking about checking model adequacy in the next set of notes.